Okay. Good evening, everyone. My name is Harini. I'm a PhD student from Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. So currently, I'm doing TA-ship in NPTEL course Watershed Hydrology, which is offered by Professor Rajendra Prasad sir from IIT Kharagpur. So in today's topic, we will be discussing about how to synthesize unit hydrographs, which is called as synthetic unit hydrographs, using different methods, and also how to develop an instantaneous unit hydrograph. So these are the main topics that we will be discussing in today's lecture, along with few problems. Okay, so what is exactly synthetic unit hydrograph? Suppose we in some areas of the catchment we don't have any rain gauge and stream gauge data available. Then in that case, what we will do is using the watershed characteristics, we will develop a unit hydrograph. Okay, what is unit hydrograph? Hydrograph is a relationship between flow, discharge, and time, right? As we have discussed earlier. So using the watershed characteristic, we will synthesize an unit hydrograph. This is called as synthetic unit hydrograph. So synthetic unit hydrograph is our main topic. So how are we developing it? As I have told you, we will have an empirical equations based on watershed characteristics. Okay, so these equations are used to get the different parameters of the unit hydrographs. And we have different methods to develop these empirical equations. So one popular method is Snyder's method. Second one is, which is most commonly used. Okay. And the second one is SCS, dimensionless method. Third one is SCS, triangular unit hydrograph method. And fourth one is time area method. We will be discussing about all these four methods. Mainly we will be concentrating on the first three methods. Okay. So first we will look into Sanders method, which is suggested by Snyder in 1938. Okay. And he developed a parametric unit hydrograph and defined it as standard unit hydrograph. So this parametric unit hydrograph, UH is unit hydrograph, that is developed is called as standard hydrograph. So we have different key elements of this hydrograph. First is effective rainfall duration. Okay. So effective rainfall duration is nothing but the duration for which the effective rainfall occurs. So as we know that in an hydrograph, that is this, we have a hydrograph as well, which is a relation between intensity and time. But in this case, we will be mainly representing the excess rainfall amount. So this value is called the excess rainfall duration. As the x-axis represents duration, this is called as excess rainfall duration. So the time for which this effective rainfall or excess rainfall is occurring is called as effective rainfall duration. And the second element is peak discharge per unit area of catchment. Okay, which is represented as QP. So as you can see, The peak of the hydrograph is the peak discharge value. And if we divide it with the catchment area, then we will have the peak discharge per unit area volume, unit area, that is QP. And the third element is time base, TB. So this also we have already represented. So all the times are in units hour, and the peak discharge per unit area is in cubic per kilometer square, and the time base is also, since it's an time unit, it's in hours. Okay, so as you can see here that TB represents the time interval between the start of the unit hydrograph to the end of the unit hydrograph. Okay, this interval gives us the base time or time base. And the fourth one is basin lag. Okay, TP. This is also in hours. So you can see that basin lag represents the uh, time interval between the centroid of the excess rainfall. So centroid will be the midpoint of the excess rainfall till the center of mass of the hydrograph. This is called as time lag. But in case of Snyder, he proposed that the time interval between the centroid of the hydrograph to the peak of the hydrograph is called as basin lag. So you can see this is the centroid of the hydrograph, and the peak of the hydrograph is this point. So this time interval is represented by basin lag. And we also have two more elements, that is width of hydrograph at 50% of peak, which is represented as W50, and its units in hours. So here in the figure, if you can see, suppose a peak discharge is QP, and since we are talking about 50% of the peak, suppose 50% of the peak is coming here, we can see that it lies on both the sides of the peak, okay, on the left hand side and right hand side of the peak, the 50% which value. Okay, so this width, this time interval between these 2 points is called as width of the hydrograph at 50% of the peak. So the last element is width of hydrograph at 75% of peak. Okay, it's represented as W75, and it is in hours. Okay, as we have, it is similar to the concept of width of hydrograph at 50% of peak. Here we are considering 75%. Suppose QP is the maximum peak as shown here, and 75% of it value is 0.75 QP, and it lies on both the sides, on the left and right side of the QP. Right, we'll first identify these 2 points, and the time interval between these 2 points is called as width of the hydrograph at 75% of peak. Now let's look into the empirical equations that are involved in the Snyder method. So the first one is the excess rainfall duration, and the basin lag is related by using this equation. And we also have few other equations like this. So the basin lag can be also calculated using this formula, TP equal to 0.75 CT into L into LCA whole power 0.3. Okay, here CT is a constant, and its value is ranging from 0.3 to 0.6, and generally it depends on the type and location of the stream. Okay, so if the slope of the stream is it is steeper, then we will have high values of CT. And L represents the length of the main stream from outlet to the divide. Suppose we have a watershed like this. Okay. So, and this is our main stream. Right. So, what does it say? Length of the main stream from outlet. This is our outlet. And the main streams, the farthest point is this. So this is called as the length of the mainstream, and LCA is the distance from the outlet to the point on the stream which is closest to the centroid of the basin. So suppose for this basin the centroid is lying here. This is the centroid point. Then we will identify the closest point on the stream to this centroid. Suppose this is the point. Then what we will do is this length on the stream is called as length of the out length distance from the outlet to the centroid of the catchment. Okay, so we will estimate the basin lag based on the characteristics of the watershed. That is, we are now here implementing that L into LCA will depend on the length and size and shape of the catchment, and CT constant depends on the type and location of the constant of the stream. Sorry. So that's why we say that whenever we are developing a synthetic hydrograph, the empirical equations are functions of watershed characteristics. Okay, so the next equation is how to determine the peak flow. Peak discharge per unit area. QP equal to 2.78 Cp by Tp. Okay, and here the Cp is a constant which ranges from 0.56 to 0.69 and is derived from the gauges or any other similar catchments values. Okay, and QP is, as I have discussed already, it's a basin lag. Okay, and Cp is a function of storage coefficient which depends on the retention and the storage of the watershed. So using Cp and Ct, we can obtain the all these key elements of the hydrograph. Okay. Suppose if we are having a unit hydrograph for T smaller duration excess rainfall and we want to calculate the unit hydrograph for T capital R duration. So that is like from smaller duration to capital R duration unit hydrograph. If we have to obtain, then what we have to do is first we will try to calculate the new basin lag. Okay, the equation is Tp dash is equal to Tp plus Tr minus small tr by 4. This is the excess rainfall duration of new unit hydrograph, and Tr is the unit hydrograph duration of old old one. So this we can also written as like this. So if they are not known, then we will try to estimate them using the length of the catchment, length of distance between the outlet and the centroid of the watershed, or with using these values, we will estimate the constant values like Cp and Ct. And then once we know that, and we have the basin lag for the new hydrograph as well, we can establish the key elements of the hydrograph as well. Okay. Also, there are other equations which is proposed by US Army Corps of Engineer in 1958. Okay. In this, the equations are the time base is given as 5.56 by QP. Okay. And the width of 50% of the peak flow is given as 2.14 by QP power 1.08, and the width of 75% edge of peak is given as 1.22 by QP whole power 1.08. Okay, so once we have these equations, we can develop the synthetic unit hydrograph. So that's it. And then we can also see that we have already discussed also that unit hydrograph is not symmetrical. You can see that it is more right skewed. So more part of the unit hydrograph is on the right hand side. So that's why before the peak, 1/3 of the volume is lying, and after the peak, 2/3 of the volume of the hydrograph is lying. So you have to remember this in case of Snyder's. So what are the advantages and disadvantages of this method is that So the advantage is that it's a very simple method. We already have the empirical relationships. So we can just easily calculate each element of the hydrograph and then develop the hydrograph. And also it's applicable for ungauge stations. But the disadvantage is mainly it's only applicable in uniform rainfall distribution case. But if there is non-uniform rainfall distribution, then it is not applicable, and is also it is suitable for small and medium size watersheds only. Okay. So the next method is SCS, dimensionless unit hydrograph method. So it is developed by Soil Conservation Service in 1975, which is now known as NRCS. Okay, and it uses an average dimensionless hydrograph derived from large number of natural unit hydrographs for watershed varying in different sizes and shapes. So, using the data from different catchments, we will develop a dimensionless unit hydrograph. What does dimensionless unit hydrograph mean? Suppose if you see in this hydrograph, the x-axis is a has time unit, okay, and y-axis has discharge unit. So it's not dimensionless. But in case of dimensionless unit hydrograph, the x and y axes doesn't have any dimension. Okay, so how we are going to obtain that is if we divide the discharge by peak discharge, then it will be a dimensionless quantity. So it is a plot between discharge by peak discharge versus time by time to peak. Okay, so in the so as you can see in this figure, you can see that x-axis is a represents the ratio of time by time to peak. Okay, and y-axis is the ratio between discharge versus discharge to peak discharge. So that means this is a dimensionless quantity and this is also a dimensionless quantity. So that's how we are obtaining a dimensionless unit hydrograph. And you can see we have two curves here. One is the dimensionless unit hydrograph, and one more is the mass curve, cumulative mass curve. So here this is our dimensionless unit hydrograph, and mass curve is obtained by the cumulative discharges values. Okay, as you can see, and it will approach 1 at the end. And the key points are that the basin lag is located approximately 20% of the time base. That is TP is equal to 0.2 TP. Okay. And also the inflection point. Inflection point, if you remember, it is where the slope of the hydrograph changes drastically. Okay. Inflection point is located at 1.7 times the time to peak. So if you see here, the inflection point can lie on the left or right hand side of the peak. So here we are talking about the right hand side inflection point. Suppose this is our inflection point, then it will lie 1.7 times the time to peak. Okay, from the start of the hydrograph. And the next point is the next method we are now going to discuss is SCS, triangular unit hydrograph method. So this is also developed by SCS, that is Soil Conservation Service, and which is now called as NRCS. Okay. Also, what it SCS suggested is that instead of going for a curve linear hydrograph, why can't we go with a triangular hydrograph? So here if you see in the figure, we are generally drawing a curve linear unit hydrograph. But instead of that, we are now here you can see it's a triangular unit hydrograph. We are assuming a we are representing curvilinear unit hydrograph by an equivalent triangular unit hydrograph. Why are we doing this is that it will ease the calculation problem. So, and also it's easy to draw straight lines compared to the curvilinear unit hydrograph, because if we know the slope of these two lines, then we can estimate the values at each and every point of the time step. Okay. So it provides a practical and efficient way to analysis, and we can get the runoff at different points of the time step. So generally, if you see here, the time ratio, the T pi TP values will range from 0 to 5. So the lower limit is 0 and the higher limit that it can go is 5. Okay. And in this case, as we have discussed previously in Snyder case, the 1/3 of the volume lies on the left hand side of the peak and 2/3 on the right hand side. But in this case, what is happening is 3/8 of the volume lies on rising limb side and 5/8 of the volume lies on recession side. Okay. So if you see here, if 3/8 of the volume will be on this side and 5/8 volume will be on the right hand side. And the empirical equations for SES triangular method are so there are a lot of equations. So first the time base formula is time to base TB is equal to 0.67 TP. Okay. And we have time of recession TR equal to total time, that is base time minus TP. So if this is the, suppose this is the base time, and if you remove only the time to peak, then we will have the time of recession, right? So a few more equations are volume of direct runoff. Q is equal to peak discharge by 2 into TP, time to peak, by plus time of recession. That is, in total, it is time to base time. So here in this, if we substitute the base time is equal to 2.67 time to peak and calculate, then the time of recession is 1.67, sorry, 1.67 times the time of peak. Okay. And next, peak discharge formula when it is in centimeter per hour, QP equal to, if we from the previous equation itself, by rearranging the terms, we'll get it like this. Okay. So since we have that TR is 1.67 times TP, just by substituting it. So overall we can say TP is 0.7 times Q by T. QP equal to 0.75 Q by TP. Okay. For unit hydrograph, what we know that excess rainfall value is 1 centimeter, right? That this implies the volume of runoff is equal to 1 centimeter, or the depth of the runoff is also equal to 1 centimeter. This implies QP equal to 0.7 times by time to peak. Okay. And QP is in units of centimeter per hour. Okay. If you want to convert into cubics, that is meter cube per second, then what do you have to do? We have to multiply with area. This area will be in kilometer square generally, and this will be in hours. The time unit will be in hours. Okay. And also they have recommended, the SAS has recommended that for large and small rural watersheds, the time lag. So that means here if you see the time basin lag, okay, that is equal to 0.6 times the TC. You might have remembered where we have studied TC. The TC is the time of concentration of the basin. Okay. So we can also write the steps that time to peak. Here if you see, this is the time to peak. Okay. It will be a sum of half of this duration of excess rainfall plus time lag. That is equal to d by 2 plus 0.6 times TC. Okay. Then we can also write these formulas, the peak discharge formulas, in this manner. Since we have new equation to peak of T, time to peak. Okay. This is when it is in centimeter per hour. In case of cubic, the peak discharge value will be, for a unit hydrograph, by rearranging the terms, the final equation will be of this form. Okay. And so here in this case, what we are doing is the time of concentration is considered as time of inflection. Okay. So TC plus D is equal to 1.7 times of TP. Here we know time of inflection, we have already given that it is 1.7 times the time of peak. Okay. So since it is given like that, then what we can say is the duration of excess rainfall is 0.133 times the time of concentration. This is our new equation. So if time of concentration and duration of the excess rainfall is known, then we can decide any required unit hydrograph. Okay. So the main disadvantage of this method is that it is only applicable for small watersheds which have an area of less than 1000 kilometers square. Okay. The next method is time area method. So in this, what we are trying to do is that we are trying to calculate the importance of, we are trying to estimate the importance of effect of time distribution of rainfall on runoff. Okay, so the central idea is that the time area method is dependent on time, the isochrones, which are the points joining the points having equal time of concentration. These points are joined together to get an isochrone. Okay. The central idea of this method is different time contours or an isochrone. Isochrone is, as I have discussed, a contour joining those points in the watershed that are separated from the outlet by same travel time. Okay. So if you see here, if this is an isochrone, that means each point on this line will be taking same amount of time to reach the outlet. Okay, each point, that means whatever the water that is falling on this points, no, it will take same time to reach the outlet. Okay, now is it clear what is isochrone? And So if that is clear, then I'll move on. So then what we will do is we will establish a time area diagram. So first we have developed the isochrones of travel time. That is like, suppose if you see here, this suppose here, if this example would be clear. So we have a dA area, and each point in this area will take time tau to reach the outlet. The each water droplet in this area will reach the outlet at in time tau. So like this, what we will do is, suppose we have time tau. So what is the area that is contributing for the water at this outlet? And it is taking time tau to reach the outlet is will be this entire area. Okay, so in tau time, whatever water falls on this part will reach the outlet, right? But the whatever water falls in this area will take lesser time than that. But if the rainfall is continuing for that duration as well, then if the rainfall is continuing for t plus some 2t time, 2 tau time, then whatever rainfall is falling here will also reach the outlet, right? So that's why this entire area will be contributing uh, for this outlet. That's why the time area graph is always increasing, and also we can see that the tau value will range from minimum 0 to maximum it can go for time of concentration, because time of concentration is that here in this case what we are saying is time of concentration, the farthest point of the basin, what the time taken by the farthest point on the basin to reach the outlet is called as time of concentration. So the maximum value that tau can go is tau c, and also similarly the area will range from 0 to tau c. Okay, it's more convenient to use a time area concentration curve because we are the after this what we can do is we can differentiate the area to get the time area concentration curve. This is more easier. That's why we will differentiate the time area diagram to get time area concentration curve. So differentiation of time area diagram gives us time area concentration curve. So from this we have seen how the time area concentration curve is generated and all. But how are we using it? How we will use it to generate the unit hydrograph? Suppose if you see, first of all, what we will do is excess rainfall hydrograph will be divided into intervals such that each interval is tau. Okay. So like this we will have the intervals based on the isochrones that we have developed for the watershed. Okay, and then we know the intensity of rainfall that is occurring in that particular time interval, and we know what area is contributing for this particular time period. Suppose for in from 0 to t1 time step, a1 area is contributing for the runoff, and the rainfall that is occurring is I naught. So similarly from T1 to T2, okay, A2 area is contributing. Okay, like that. So the overall runoff is calculated by Qi equal to at each time step. So the time step is I, sorry, let me write this equation clearly. So at any time step I, the runoff will be sigma I equal to 1 to j aj times I of I minus j. Suppose for time step 2, what we will do is Q2 is equal to, so first value is A2 into I times of So for J equal to 2, uh, so I have written the equation wrong. Let me correct it once again. So for any time step, the discharge value Qi is equal to sigma of J equal to 1 to I, Aj, intensity of rainfall, I minus J. Okay. So Aj is the area that contributes for the runoff in that particular time step. Okay. For suppose I equal to 2, then Q2 is equal to, here first J equal to 1 we will consider A1. So that is this time step into I of 2 minus 1. Okay. Plus A2 I of 2 minus 2. That is A1 I1 plus A2 I0. Okay. So like this, we have to calculate the discharge values at each time step to get the unit hydrograph using the time area method. Now let's look into few problems related to this. So the first question is this Snyder defined a standard unit hydrograph as one whose rainfall duration TR is related to base time by basin lag TP by. So we all know that TR equal to TP by 5.5. Therefore, by rearranging TP equal to 5.5 times of TR. Okay. Then the next question is different synthetic unit hydrographs are derived based on option A, watershed characteristics, option B. This I have told that it depends on watershed characteristic. Option B is geomorphology. Sorry. So option B is geomorphological characteristics and hydrograph characteristics. So we also know that in Snyder's, it depends on length and the length of the mainstream like that. So that's why we can say it depends on geomorphological characteristics as well. And a synthetic unit hydrograph can also be developed by dimensionless unit hydrograph. Okay. This also we have seen SCS dimensionless unit hydrograph we know. So that is also correct. And models of catchment storage. So we know that CP is a function of storage term. So that's why we say all the four options are correct. So the next question is a peak discharge per unit area of a drainage basin is 0.45. So that is QP equal to 0.45 cubic per kilometer square. What, according to Snyder's method, what is the width of 50% of peak? So we know that from the formula, W50 is 2.14 by QP power 1.08. So 2.14 by QP is 0.45 whole power 1.08. That is equal to, after doing calculation, it's 5.07 hours. Okay. So the width of synthetic unit hydrograph are distributed with respect to peak as one third of the widths are distributed before the peak. Second option is two-thirds of the widths are distributed before the peak. Third option is one third of the widths are distributed after the peak. Fourth option is two-thirds of the widths are distributed after the peak. So as you remember, the unit hydrographs are right skew. So more volume is on the right hand side. Okay. And we also discussed that one third of it will be lying on the left hand side of the peak and two-third volume will be lying on the right hand side. So from this, the option A and D are correct. So the next question is watershed A has following, sorry, watershed A having the 2-hour unit hydrograph derived from observed rainfall and runoff of an isolated storm on it has following characteristics. So let me write it down. Watershed A, the 2-hour unit hydrograph means D is equal to 2 hour, and the watershed characteristics are basin lag is defined as TP, that is equal to 24 hours. Peak discharge QP is 50 meter cube per second. Area of the catchment is 700 kilometers square. Length of the mainstream is 30 kilometer. Distance between the outlet and the centroid of the catchment is 15 kilometers. And they have said that a watershed B, which is hydrologically similar to watershed A, has the following characteristic. They have given the characteristics of that also, and they are asking us to what are they asking? Estimate the peak of the 4-hour synthetic unit hydrograph for watershed B using Snyder's method. So, as we have discussed previously, if the two watersheds are hydrologically similar, then what we can do is the constant terms will be same, that is Cp and Ct. So, first we need to calculate Cp and Ct of the watershed A, since we don't know. But we have other elements values, right? So, first let's check uh, what is the Tp value. 21 by 22 Tp. So here Tp dash is 24 into Tp plus, we know the time of excess rainfall is given as 2 hours. Okay. So once you calculate this, Tp is obtained as 24.1 hours. So using the new Tp, we will calculate the Ct. LLCA whole power 0.3. 24.1 by 0.75 into 30 into 15 whole power 0.3. Okay. So we know length of the mainstream is 30 and the distance between the outlet and the centroid is 15. Okay. 0.75 into 30 into 15 whole power 0.3. That is 51.4. Sorry. So that is 5 point. After calculation, it is coming as 5.14. Okay. And then we will estimate Cp using formula Qp P dash by 2.78. So since Qp is the small qp is the peak discharge per unit area of the catchment, peak discharge is given as 50 meter cube per second. So we have to divide by area. Okay. Into Tp dash by 2.78. Zero 0.619. Okay, this is a Cp value. Now for watershed B, how do we calculate is the length of the watershed is given as 120 kilometers. Okay. And length of the mainstream is given as 120 kilometer. Distance between this outlet and the centroid is given as 100 kilometer. Area is 1200 kilometer and the kilometer square, and the duration of the excess rainfall or T capital R is 4 hours they have given. So now they are asking us to estimate the peak discharge. Okay. So we know we have to first calculate Tp. It is 0.75 Ct into LLCA whole power 0.3. That is 0.75 into Ct value. It will be same as the watershed A because both watershed A and B are hydrologically similar. That is 5.14. 5.14 into 120 into 100 whole power 0.3. So 120 into 100 whole power 0.3 into 5.14 into 0.75. That is 64.53 hours. Okay. Now we'll try to estimate the duration of excess rainfall. That is TP by 5.5. Okay. 64.53 by 5.5. 11.73 hours. So this is not same as the duration of excess rainfall, that is 4 hours in our case. So we have to estimate the new TP, that TP dash is equal to TP minus is equal to 60 point minus 11.73 minus 4 by 4. 62.59 hours. Okay. Then we will estimate the peak discharge using the formula 2.78 Cp by T. And we have already estimated Cp value, that is 0.619, same as previous watershed, that is watershed A, by 62.59. Okay, 2.78 into 0.1619 divided by 62.59. So that is approximately equal to 0.027 meter cube per second per kilometer square. So if you want to find the peak discharge in cumex, we have to multiply this value with area. So 0.027 into area of the catchment is given as 1200 kilometer square into 1200. That is approximately 33 cumex. So once you multiply with area, we'll get the peak discharge value. So the next question is, watershed A having the 2-hour unit hydrograph derived from observed rainfall and runoff of an isolated storm on it has following characteristics. So, and watershed, these are the characteristics that they have given, and the watershed B, which is hydrological similar to watershed A, has the following characteristics. These are the characteristics. Then they are asking us to calculate the time of rising or time of peak in hours. Okay, as we have previously seen already that for watershed A, the CT value is 5.14 and CP is 0.619. So this will be applicable for watershed B since they are hydrologically similar. And the terms, so this is for watershed B. Okay. Area is this, length is 120 kilometer, LC is 100 kilometer. So time to peak or time of rising is TP dash is equal to how much we have to find. But initially we will find TP, that is 0.75 CT into LLC whole power 0.3, 0.75 into 5.14, 120 into 100 whole power 0.3. It is equal to 64.53 hours. This is TP, okay? And TR, duration of excess rainfall, is TP by 5.5. That is 64.53 by 5.5. That is 11.73 hours. So therefore, we have to estimate the time to peak of this new hydrograph since it is not same as the excess rainfall duration of 4 hours. TP minus TR, as we have seen already in the previous calculations, is 11.573 minus 4 by 4 is equal to 62.59 hours. 0.59 hours is the answer. Okay. The next question is also similar. Watershed A has the basin characteristics they have given, and watershed B is similar to watershed A, and their basin, few of the basin characteristics is given, and they are asking us to find the time base. Okay, so CT is 5.14 for watershed B, as we have solved in previous problems, and CP is 0.619, and the time. And also you remember that peak flow is calculated as 0.0. This is the value. Peak flow per unit area is 0.027 cubic per kilometer square. Okay. And the time base is given as 5.56 by QP. 5.56 by 0.027. That is approximately equal to 205.92 hours. Okay. So the next question is the x-axis of the dimensionless unit hydrograph usually consists of. So if you remember, the unit hydrograph looks like the x-axis has T by TP, this is time ratio, and y-axis has Q by QP, discharge by peak discharge ratio, that is discharge ratio. So the question they are asking for the x-axis of the dimensionless unit hydrograph usually consists of. That means it's time ratio. Okay, so the next question is the time base of SAS triangular method is dash times the time to peak. So as you might have remember earlier I have mentioned that a time base of SAS triangular hydrograph, unit hydrograph is equal to 2.67 times the time of peak. Okay, so the answer is option A. So the next question is for a basin area of 3 kilometers square, the time of concentration is given as 1.25 hours. Okay, and for a 1 hour triangular synthetic hydrograph means the duration of excess rainfall is 1 hour. What is the time to peak or time of raising in hours? So TP is equal to, as you might have remembered, T by 2 plus 0.6 times the TC value. So that is 1 by 2 plus 0.6 into TC is 1.25. So when I do the calculation, the answer is 1.25 hours. Is that clear? If you guys have any questions, you can stop me in between and ask the question. Either raise the hand or can speak out. Okay. The next question is a catchment is having an area of 3 kilometer square. Area is 3 kilometer square and time of concentration is 1.25 hours. For a 1 hour triangular synthetic hydrograph, the peak discharge is dash. This we have to estimate the peak discharge. Okay. So for 1 hour duration, for 1 hour triangular synthetic hydrograph means the duration of excess rainfall is 1 hour. Okay. So the peak discharge, the formula for peak discharge is 2.78 A by TP. So we know 2.7 A by, to estimate TP, formula is T by 2 plus 0.6 times TC. So 2.78 into 3 by 2 by 2 plus 0.6 into 1.25. Answer will be 2 2.78 into 3 divided by 1.24. 6.67 meter cube per second. Okay. So here, since we are multiplying it with area term, the units will be only in cubics. Okay. So the next question is, the area of the catchment is 3 kilometers square and the time of concentration is given as 1.25 hours. For a 1 hour synthetic hydrograph, for a 1 hour triangular synthetic hydrograph, that means T is equal to 1 hour. The time base, estimate the time base. Okay, the time base is equal to 2.67 is the peak of time. Okay, so 2.67 times D by 2 plus 0.6 times TC. So 1 by 2. Okay, in the earlier equation also this is 1 by 2. 1 by 2 plus 0.6 times 1.25. So the value will be 3.34 hours. Okay, approximately. The base time will be 3.24 hours. So now that we know how can we construct the unit hydrograph. Okay, so we know the total base time is 3.34 hours and the time to peak is 1.25 and the peak value is how much? 6.67 meter cube per second. So this is how our triangle will look at. Triangular synthetic unit hydrograph will look like. So like that, for in case of SCS triangular method, if we know time base, peak time to peak and peak discharge, we can construct a unit hydrograph because we know in case of unit hydrograph, the first term will be 0, 0. At time step 0, the discharge also will be 0. And in case of the time step equal to time base, okay, that is 3.34 hours. The discharge also will become 0 because there is no base flow. So since we know this point as well, this point value coordinates will be 1.25, comma 6.67, right? So using this, the coordinates of these 2 points, 0a, we can estimate the slope of OA, and similarly using the coordinates of A and B, we can estimate the slope of AB line. So using that, we can calculate the discharge values, okay, of the unit hydrograph at this intermediate points as well. Is this clear? Any questions related to this? So I'll move on to the next questions. The next problem is a 90 kilometer square catchment. So the area of the catchment is 90 kilometer square. Has 4-hour unit hydrograph. That means T is 4-hour, which can be approximated as triangle. The P coordinate of the unit hydrograph is QP is 10 meter cube per second. What is the base time? So here if you see, they're saying the unit hydrograph is estimated as a triangle. And we know this term base time is, what is the base time they are asking. And time to peak is 10 meter cube per second. So we know that once we calculate the area of this unit hydrograph, it should equal to, it should equal to the volume of, it will give us the volume of runoff. Okay, once we divide it with area of catchment, it should be equal to the excess rainfall value. For unit hydrograph, it should be 1 centimeters. So the area of the unit hydrograph is half into base into height because it's a triangle. Half into base is TB into height. That is 10 meters square per second. And this will be, should be equal to volume of runoff. That should be equal to volume. Sorry, here in the case, it should be equal to volume of direct runoff. So it will be directly equal to volume of excess rainfall. That is how we will calculate excess rainfall. We know for unit hydrograph, 1 centimeter rainfall is occurring in 4 hours. So 1 centimeter is 1 by 100 meter into area of the catchment is 90 kilometer square. Suppose if we convert everything in meter square, we have to, sorry, in terms of meters, we have to multiply it with 10 power 6. So then the TB is, once we do the calculations, it's 18 into 10 power 4 seconds. So to convert into hours, we have to divide by 3600. That is equal to 50 hours. So the time base of this triangular unit hydrograph will be equal to 50 hours. Okay. The next question is the time of concentration of our catchment area is, time of concentration is given as 26 hours. The time to peak of a 4 hour triangular shape the unit hydrograph is how much they are asking. So in this case, how we will calculate? We know that time to peak is equal to T by 2 plus 0.6 times Tc. Okay. And since they have mentioned it's a 4 hour triangular shaped unit hydrograph, the duration of excess rainfall is 4 hours. Okay. So once you substitute this in this formula, 4 by 2 plus 0.6 into 26. So the time to peak is 0.6 into 26 plus 2. 17.6 hours. Next question is, if the duration of a rainfall event is 2 hours, that is D equal to 2 hours, according to SES triangular unit hydrograph, the time of concentration is how much? So if you remember, the last formula that we have discussed in SES triangular method is that D equal to 0.133 of TC. Okay. So TC equal to D by 0.133. So TC equal to T is 2 hours, 0.133 is equal to 2 divided by 0.133. Approximately 15.04 hours. So the option is D. So the next question is, in a triangular unit hydrograph, the time to peak flow is typically located at. So if you remember, the option is 1/3 of the total duration, half of the total duration, 2/3 of the total duration, and 3/4 of the total duration. In case of triangular unit hydrograph, the time to peak is typically located at 1/3 of the total duration. Okay. So now let's look into what is in instantaneous unit hydrograph. Okay. The next topic. So till now we have seen how we will synthetically develop a unit hydrograph when we don't have observed stream flow or rainfall data at a particular station. Okay, using empirical relationships that are developed based on the watershed characteristics. We have seen 4 types of method, and now we will be discussing about the instantaneous unit hydrographs. Okay, so what does instantaneous unit hydrograph means? Suppose here whenever we are seeing the unit the hydrograph. Okay, the excess rainfall, suppose we are saying excess rainfall is occurring for d hour duration. So based on that d hour duration excess rainfall, there is some hydrograph that is generating, which is a response. Okay, suppose in case of instantaneous unit hydrograph, instantaneous unit hydrograph, if the duration of this excess rainfall is changing, the unit hydrograph is changing. So that's why what we are trying to do here is that we want a unit hydrograph that is independent of the duration of excess rainfall. Develop a unit hydrograph independent of excess rainfall duration. Okay. So this is our main objective. In this case, what we are doing is uh, we are developing an instantaneous unit hydrograph. It is used to estimate the response of the watershed to a unit input of rainfall at a very short duration. Okay, this duration is, as you can see here, in the case of A, the duration is suppose D. As we are moving towards B, C, and D, the duration of the hydrograph is decreasing. So we are trying to estimate the hydrograph. When same amount of rainfall is occurring in shorter duration, so the peak of the discharge is also increasing, and also you can see the time. So if you see, time to peak is also decreasing. Time to peak is decreasing and peak of the discharge is increasing. So here in the case of uh, excess rainfall occurring for d-hour duration, in case of A, you see the peak is over here and the time to peak is here. And in case of D point, which is occurring for very short duration, the time to peak is only at this point, and also the peak is also increasing, right? So, so dependence of unit hydrograph on duration of excess rainfall is avoided by letting D be diminished indefinitely. Therefore, the unit hydrograph obtained in this case is called instantaneous unit hydrograph. Okay. So the one unit hydrograph picture instantaneous unit hydrograph is also represented as IUH. Here what we are doing is 1 cent. So 1 centimeter is the excess rainfall in a unit hydrograph, right? If it is occurring for zero duration, since we cannot see it is occurring for zero duration, what we will try to do is, in this case, we will limit t tends to 0 h of d comma t. Okay. So, and also we have some terms in this IUH, instantaneous unit hydrograph. That is, first one is unit impulse. So, unit impulse is the spike. If you see here, you can see a spike that is occurring for a very short duration. That is a unit impulse. Okay. So it's defined as del t equal to limit t tends to 0 I of t comma t. Okay. This is direct delta or unit pulse function. And the main properties of this is that the area under this unit pulse will be always equal to 1, okay, from minus infinity to infinity, and at any instant delta t equal to 0 for t not equal to 0. Okay, so it is this term is always 0 except at the point where the impulse is occurring. Okay, so if we have an impulse, suppose we are saying that rainfall is coming in an impulse or instant. Okay, we will have some response that is called as impulse response. This response is the hydrograph in our case. Okay, if unit input is applied instantaneously at time tau, okay, suppose this is time tau, unit impulse is applied. Okay, the response of the system at time later t is given as its impulse response function. Okay, and in this case, what we do is if the I tau is the intensity of the rainfall and is occurring for a infinitesimally small time, then I tau into theta is the input during the interval. Since here we can see that this is this is a unit impulse occurring. Okay, so for that, if this is the unit impulse response function for I tau intensity rainfall or intensity impulse, then the reaction will be 0 tt I tau h of t minus tau into dt d tau. Okay, so this is obtained from convolution theorem. Okay, from we can derive this. And in this case, h of tau is equal to 0 for tau less than 0. For tau less than 0, that is here, there is no response. Okay, that's why h of tau is 0. And alternative form is q of t is equal to integral 0 to t h of tau I of t minus tau theta. Okay, with h of tau greater than 0 for h of t greater than for t greater than or equal to 0, and limit t tends to infinity h of t is equal to 0. So there are few important properties related to IUH. The first one is the response function is always in between 0 to a positive volume. For t greater than 0. Okay, and h of t is equal to 0 for t less than or equal to 0, and h of t tends to 0 for t tends to infinity. You can see at the infinity duration that h of t is almost touching the 0 point. Okay, and one more important property is if you integrate h of t dt is equal to unit depth over catchment. Okay, and you can see that in this case always the time of peak is less than time to centroid because the hydrograph is screwed towards, right? The centroid will be here and time to peak is here, so it's always less. So now we can see how to derive the unit hydrograph. There are many methods related to it. First we will concentrate on how to derive it using a Hess hydrograph. Okay, suppose we have two S hydrograph. If you remember, S hydrograph is obtained when you have a like when you infinitesimally add a unit hydrograph. Okay, so like when you infinitesimally superimpose a unit hydrograph, we will get an S hydrograph. Okay, the shape also will be in the S shape, and you can see the above the hydrograph is also extending for an infinitesimal time, which has an intensity of 1 centimeter per hour. Okay, so first what we will do is we will offset the S hydrograph by dt time. Okay, then the ordinates of dt hour unit hydrograph are obtained using the formula S of t minus S of t minus dt. by I into dt. Okay. Here, in the case of unit hydrograph only in the case of unit hydrograph, the intensity will be 1 centimeter per hour. Otherwise, in other case, there will be some intensity going on. So, if dt is tending to 0, then it will give us instantaneous unit hydrograph. So, we will apply dt is equal to 0 condition, s of t minus f of t minus dt by, and also I equal to 1 for unit hydrograph, right? So it's dt. So that is equal to this. If you see the limit dt tends to 0, s of t minus dt by dt is differentiation of s hydrograph with respect to time. If you remember this formula. Okay, if the S hydrograph is derived from unit hydrograph of excess rainfall of 1 centimeter per hour, we have written it here already. The slope of S hydrograph will give us the instantaneous unit hydrograph coordinates. So here you can see that that's what we have derived. Okay, the slope of the S hydrograph is giving us the ordinates of instantaneous unit hydrograph. So ds is equal to h of t into dt. Suppose if we integrate between two sections 1 and 2, okay, ds is equal to t1, t2, h of t dt. So that is s2 minus s1 equal to integral t1, t2, h of t dt. Okay. So if h of t is a linear within 1 to 2 and they are of small values, then what we can do is delta t is equal to t2 minus t1, and h of t can be represented by this formula. Okay. Then s2 minus s1 is equal to h of t2 plus h of t1 by 2 into t2 minus t1. So here what we can do is h of t1 comma t. So the ordinate of unit hydrograph of d hour duration is equal to, what we can write is average of instantaneous unit hydrograph at t plus instantaneous unit hydrograph at d minus t. Okay, so that means unit IUH lagged by d1 hour can be used to generate d1 hour unit hydrograph. Okay, so the next small topic is the distribution graph, which is also called as Bernard distribution graph. So it gives us the variation of unit hydrograph. Primarily a d-hour unit hydrograph with coordinates showing percentage of runoff occurring in successive periods of equal time interval of d-hour. Suppose we have each interval is d-hour, okay? T1, T2, like this we have T3, okay? And we will see percentage of runoff that is occurring in this T1 interval, okay? In this T1 interval, and in between T1 to T2, how much percentage of runoff is occurring? Suppose total volume of runoff is 100 meter cube per second. If 10 meter per cube per second is occurring from 0 to T1 interval, that means 10 by 100 into 100. That is 10% of runoff volume is generated in T1 hour from 0 to T1. Similarly, like from T1 to T2, we will calculate how much percentage of runoff is generated. So it is based on linear theory and is useful in comparing runoff characteristics of different catchments. So if most of the volume is running in the initial time period, that means we have like the response of the catchment is taking less time compared to the other catchment, right? So we should be very careful. If there is a huge amount of rainfall is occurring, in those cases, the flooding will occur in a very short time period. So now let's look into few other problems or questions. The next question is an instantaneous unit hydrograph is hydrograph of option A, unit duration and unit infinitesimally small excess rainfall. Option B is infinitesimally small duration and unit excess rainfall. Option C is infinitesimally small duration and of unit excess rainfall of an infinitely small area. Option D is unit rainfall excess on an infinitely small area. So if you remember, the we are mainly putting constraint on the duration of excess rainfall. The if the duration the excess rainfall is occurring for a infinitesimally small duration and the total excess rainfall amount is equal to 1 unit, then we are calling it as instantaneous unit hydrograph. So the option is option B. In case of time area method, for deriving a synthetic unit hydrograph, the main principle is, so as you might have remember, in case of time area method, if this is the outlet, we are trying to develop uh, isochrones. That means the points having same equal amount of time of travel. So this one, all the points lying on this line will take time tau to reach the outlet. Similarly, this will reach time 2t, 2 tau, like that. So we are trying to generate a isochrone. So basically, the main principle is isochrone, and based on that, we are calculating the unit hydrograph. Also, the next question is the intensity and unit hydrograph and detail are the Ito, H, and Dito are the intensity of rainfall, the ordinates of hydrograph, and the infinitesimally small time respectively. Then the resulting direct runoff from the instantaneous unit hydrograph will be. So if you remember, I have written the formula. So this will be our resulting direct runoff from an instantaneous unit hydrograph. So the next question is the graph between the percentage of runoff occurring in successive period of equal time interval of t hour and time interval is known as. So if you remember, at each time interval we are calculating the percentage of runoff in case of distribution graph. Okay, time is also equally divided for t hours. Okay, so that is distribution graph. Hydrograph is a relation between discharge and time, not percentage of discharge. Snyder graph you have seen, percentage distribution graph. The next question is, in hydrology, the step response function is commonly called as. So if you remember, in case of S hydrograph, if you see, the excess rainfall is uh, given as a box, okay? And the response for this box is our S hydrograph. Okay, here this is the input is excess rainfall, which is having an intensity of 1 centimeter per hour, and this box kind of inputs are called as step functions. Okay, step inputs. So for this, the response generated by the catchment is our step response function. So in this case, the S hydrograph is a step response function in hydrology. Okay, so uh, these are the problems that we are covering in this week, and also we have talked about how to synthetically develop a unit hydrograph using Snyder's method, SCS dimensionless method, SCS triangular unit hydrograph method, and time area method. So we have also discussed of instantaneous unit hydrograph and how we can develop a instantaneous unit hydrograph using S hydrograph. Okay. Is there any questions related to this topic? If there are any questions, I still have some time left. I can answer those questions. So if there are no questions, we can end the session. Thank you for attending the session.